Okay, so forward, what do we know? We know this is 5840. It's in this direction. We can just use this, right? Does everybody see that? 5840, the forward azimuth going in this direction from A to B clockwise is going to be 58 degrees, 40 minutes. Does everybody see that? So let's go ahead and we'll start our table like we did on the bottom. So we're going to start with this forward azimuth of 5840. So we want to find what? First thing we got to do is find the back azimuth. So how could we get that in this case? This one's pretty, how would we get it? Add 180. Does everybody see that? So forward azimuth, we want to go the other direction. We want to swing this around, so let's add 180. And again, I know I said this last week, but grab your calculators and just keep and work alongside. Because just getting used to punching things in also helps too. You'll start to see the cadence in the calculation. So I got 238.40, and that is now what? That's the back azimuth. So 238.40. Okay, we good there? Yeah. All right, so let's follow the formula. And what did the formula on the sheet say? All right, I'll throw it up on there. So we're going clockwise. So we're going to be subtracting. Okay, we're going to be subtracting. So we got the back azimuth. We're going to subtract the interior angle. So minus 102.11. 102.11. That's the angle, and we're subtracting. Punch that up. What do you get? I should hear lots of voices all agreeing with whatever we're punching up. So 136.29. How's that sound? 136.29 degrees, and that is now the forward azimuth. So from the pieces, how about this? We started with a forward azimuth. We took 180 degrees to get the back azimuth, and now we're just following the formula to subtract the interior angle because we're going to get B to C. So B to C's forward azimuth is 136. 29 minutes. AB. All right, I'll let everybody catch up. Is everybody good to get there? Yes, yes. If you're not, say, Bob, take a step back. So you can holler at me. I'm working for you. So, okay. All right. So what do we need to do next? We want to take this forward azimuth and we want to turn it into what? What's its back azimuth? Because we need that. We need its back azimuth so we can go to the next angle. So what do? What would you say on this one? Add 180. Okay. So let's add 180. And hopefully everyone's seeing that your calculator just kind of has this running scroll. So it's just the answer you had left in there last time is going to be sitting there waiting for you to punch the next number in. So 316.29? Yeah. Okay. So that's the back azimuth. 316.29. Okay, what do we do next?
Minus the 104.42.
42, minus the 104.42. Everybody see that? So just follow the formula. So we've got the back azimuth. Let's minus the interior angle. Minus 104.42. What do you got?
173 and 47.
Let's see here. Did I punch it in wrong? 316.29. What was that? Let's try 316.29 minus 4. what? How about this? Anybody get anything different?
I got 211.57.
I got 211.47. Was that?
I got 211.
Try punch it. See, Lozandro,
211.
punch that in again. See if you got it. Lozandro, are you okay?
Yeah, I got 211.
211.47. Okay, so 211.47 is now the forward azimuth of C to D. Okay. All right, so we'll bring this up so I can keep it on the sheet here. So let's go 211. Forward AZ. Okay, so anticipating now, this is one that we gotta kind of think about a little bit. So the 211, we've got to get the back azimuth, right? So we've got the forward azimuth for this one. We want the back azimuth for it. What could we do? We could do two things, right? What did we say last week? We could add 180 degrees to this, right? We could add 180 degrees. It's going to give us something bigger than 360, right? Or our brains might think, hey, look, this is a real shallow angle here. It's going to be less. What if I subtracted 211.47? I could get that angle back here. This is just one of the parts of the solution you just kind of have to anticipate a little bit. Let's just for sake of argument, let's go ahead and add it. Let's add it and make it a big angle. So let's just go ahead and keep doing what we've been doing. Let's add 180. $211.47 plus. So 391. So we got this big angle. It's even bigger than 360. We've wrapped around the clock and we've gone past 391 degrees 47 minutes. But we've said in azimuth, when we're dealing with azimuths, it's okay. It's the same. It's heading in the same direction. So we can have something that's bigger than 360. Okay. So what do? Follow the formula, right? So this is our back azimuth at 391. Minutes. Okay, what do? Subtract the interior angle, which is what, 113? 113 degrees, 05 minutes. Subtract that. Numbers, what do we got? I got my calc. What do you get? Throw some numbers out. What do you got? Anybody?
278.42.
278.42. Okay. And that's a forward. We're rolling here. All right, 278. 42. Okay. So back azimuth, we could add. So just think about this. It's 180 degrees opposite to this. We could go ahead and add 180 to this and get a big angle. Let's go ahead. Let's try it. Let's see what we got. So let's add 180. $458.42. And that's what, back azimuth? This is C to D. Okay, what do? Just follow the pattern, right? Subtract the interior angle, right? So let's subtract 118.34. Numbers?
340.08.
Any other takers? 340.08? 340.08, okay, yep. And that's the forward azimuth of E to A. And let's move this one up here. Just keep it going here. So 340 degrees, 08 minutes. Okay, let's try something. Let's keep doing what we've been doing. So far, every time we wanted to turn a forward azimuth into a back azimuth, we've added 180 to it, right? Plus 180, plus 180, plus 180. Let's go ahead and let's just see what happens. This just becomes the little place where we might have to make a little tweak to this. So let's just say plus 180. So 340 plus. I got 520.08. And that's now the back azimuth of what? E to A. That's this one here, 520.08. Okay. So let's say for this problem we've got the distances, we've got the bearings, and we prefigured all of the forward azimuths. Interestingly enough, and if you look on the sheet that I handed out, the computations with latitudes, you can use either the bearing or the azimuth. You can use either of the angles. So as we solve this today, we're going to be able to either use the bearing as it's given or the azimuth that it's given, just as it's written. You don't have to do any changes to any of the numbers as we run the calculations. We can just punch these in our calculator as the numbers are. So I just handed out a table, and the table is basically the crib sheet, or at least the means of us translating all of this data into something that we can use. Let's take a look at this table real quick, and we're going to talk about a couple of pieces. So this table, it basically, if you fill it in and you run the calcs, we're going to end up getting the northings and the eastings for all of our points. So let's just look on the table that we have at what we're talking about. So station is going to end up being, and you guys can fill one out. This is going to be what we're going to do, is we're going to fill out one of these tables. We're going to run these calculations, and we're going to figure out some coordinates here. Because I think in the problem, does it give us 1,000, 1,000? I believe it does. So let's do this. Does everybody got everything charted? You guys, everybody okay? Got numbers? So let's grab the table, one of the sheets that I gave you, and let's get this ready to go, because we're going to be entering and calculating all sorts of numbers in the table. So let's just say right here, what we want to end up doing is we're going to call each of these points, or the station, these will be the point numbers, A, B, C, D, and E. Because we got 5 points on this sheet. Now when we say the course, and something to just take a look at, A and B and C and D, everything is all grayed out on the table. By the time we get to the end, A is going to have a coordinate. B is going to have a coordinate. Each of these points will have coordinates after we run all the calculations. So the course is going to be between the 2 points. So our course in this case is going to be A to B. This will be B to C, and on down. C to D, D to E. And let's go ahead down here and just add an extra A, because we're going to close the traverse, so this is going to be E to A. By the time we work all the way around our traverse, we're hoping to fall back on the same point A and calculate the same coordinate. So the premise of this is we're going to use this table to walk around the traverse and calculate the different departures and latitudes. So let's go ahead and let's get the distances in between each of these, so you guys can work on that on each of the legs. So A to B is 164.95 feet. Feet. And we'll jump back real quick to the sketch. So let's say our crews were in the parking lot, or our crews were out in a cornfield somewhere. And you guys have kind of done a traverse already when we did the triangles in the hallways where you sat on a point, you zero set on one of the lines, and then you turn the angle and measure the distance. That's essentially what happened to get to these points. So each time they set up on the next point, they backsighted and zero set on the instrument. They swung it and turned an angle, measured 102.11. Then they hit measure and shot a distance. So that's how this traverse was assembled. It was, let's just say for conversation's sake, for application's sake. So they made 1, 2, 3, 4, 5 setups. They backsighted and zero set on the back point, and then they turned the angle. So one of the first things that we could do is, what did you kind of learn, at least in using the instrument so far, in terms of variations in accuracy? Does it have a little bit of movement in it? It's pretty hard to know exactly degrees, minutes, and seconds when you zero set and you shoot something. If Cynthia and I went out and we set up on a point and we zero set and shot an angle, if Patrick and Kenneth did the same thing, set up on the same point and measured an angle, do you think they'd get the exact same number that that Cynthia and I got? Probably not, right? Because all of the things we talked about in the first couple of weeks, environmental factors, human error, your eyeball, your focus, what did I start on? So we're all going to get different angles. Same with the distance too, right? If Cynthia and I shot it and we got 164.95, Patrick and Kenneth made a shot at, who knows if the prism had a little bit of movement, could have been windy, maybe they got 164.92, right? So a traverse is not a hard, fast, this is what the number is. A traverse is whatever you and your crew or your teammates shot it at, and everybody's going to be different. So building that into this, we have to figure out, well, what's right? What happens if we all went around this traverse and everybody got different numbers? It doesn't mean that anybody's right or wrong, but are we going to be accurate and precise? So one thing we should probably do is, let's take a look at all 5 of these angles in this traverse, and let's see if they closed, or all the angles together. So if we go into the table, grab your calculators, let's just see how good this crew was. Let's see, did all 5 of the angles add up to, what's our number? I probably don't remember off the top of your head, but it'd be 540, right? So we've got 180 times the number of sides minus 2. So it's 180 times 5 minus 2 would be 3, 180. So we should be hoping that we get 540. If it was perfect, it'd be 540. Let's add them up and let's see what we get here. Oh, and I'm sorry. Where do we put our angles? Let's go ahead. Actually, we won't do that on the table. Let's just go through this and add these up here real quick. Sorry about that. Oh. Tell me what you got. 540. All right. Well, so we got a crew that's on their game. So that traverse close. So the sum of all the angles came to 540. So we're starting with a really good traverse. So that's good. But what else could vary in this? So that's great. All the angles turn. How about the distances? That's what we're going to take a look at. Could have been a little difference of each of the legs of the traverse. Maybe there's some variation in there. So we're gonna work through and see how it worked. How did all the shots work out? So let's look at the table. So the next thing we're gonna do is the bearing or the azimuth. Bearing or the azimuth. Let's do the azimuths. Let's do the azimuths. So what we can do is jump into our table, just look at AB. So the azimuth for AB, we just have to fill in the blank, whatever it says. A to B, the azimuth is 71 degrees, 11 minutes. You guys can run around the shape, same thing. So B looks like 149, or B to C, 149. Okay. So we'll get all 5 of those azimuths punched in. Okay, now looking on the handout that I gave you, but also I've built the table. So the table pretty much tells you which sign to use. So when we go back to our triangle and we said the latitudes are going to use the cosine of either the bearing or the azimuth, we've got it right here for us. The latitude's here, which is going to be in the north-south direction. If we're using a bearing, we're just going to take the cosine of it. So we want to use the cosine times the length. That's going to be our distance. The cosine of this times the distance between the 2 points is going to give us the change in latitude to get between these 2 points. So just go ahead and punch it into your calculator. What is the cosine of 7111? Times the length, 164.95. Holler out a number when you get it. Some of your calculators might be able to take the 71 degrees 11 minutes and put it right in. Some you might have to convert it to a decimal. Everybody's calculator is different. Bless you. Numbers, anybody? Cosine of 7111 times 164.95. Who's got something?
53.20.
5320, Lozandra says. Anybody? We got a match? Anybody? Kenneth shaking? Eduardo shaking? Okay. So 5320. And that's in feet. So if we went back to the example, everybody with me? How are we doing back there, okay? $520.08. What's the last thing? So we can check. That's one thing about running these traverses. We can check our answer. We can always see if we're going to match. So we should come up with what? The forward azimuth for this one should end up being 58.40. Well, let's see what's going to happen here because we got this really big angle here. But let's go ahead and just follow the formula and do what it says. So let's take away, we've got to subtract what? The 101.28. So we got the back azimuth minus 101 degrees, 28 minutes. And what do we get? So we take away 101. Okay, what do you get? Who's got a number?
418.
It's big, right? Yep. 418.40, Lozano? 418.40? 418 degrees, 40 minutes. So this would be the forward azimuth of A to B. But what do we see about this? That's kind of big, right? we've said we can have azimuths bigger than 360, but let's just take a look at kind of what we're looking at on the picture here. The forward azimuth when we started, when we just took this bearing from north to east, this was a simple one, right? It's in the first quadrant, so it's just going to be 5840. Now the numbers look kind of good here. What could we do to this number to see if it matches with this? Minus 360, right? Does everybody see that? A forward azimuth can have 360 added to it, right? So what if we took away 360 off of this one? This 41840 is in this direction. It's just big. Let's take 360 away from it. Minus 360. 5840?
Yeah.
As it should be. Check mark, gold star. We got it. Oops, that's as far as I can go. Okay. How do we feel? Kinda?
Better.
It's better, okay, better. Can we go, those that had the 3 or the 4, maybe we're at a 5 or a 6. It's just really sitting down and doing it. That's really what this is. It's kind of a puzzle, but it's just following the same cadence. Just staying in cadence and just working around the shape. And we could do a little comparison here too if we wanted to, because I had solved 810. I don't know if I can get both of these on the screen here. Maybe I can. Maybe let's just take a look at a comparison between the two. So 810 counterclockwise versus 810 clockwise. Let's make this focus. And we won't run any calcs. Let's just kind of discuss some of the findings and some of the numbers that we have. So when we look at this azimuth going in one direction, 278.42, and we look what we just calculate, 278.42. So the azimuth is still the same. Take a look at this one, 340.08 going counterclockwise. 340.08. How about this one? 316.29. 316.29. So there's a couple of differences in here, right? I'm seeing right here. We kept adding 180 to everything that we were doing. So we had this azimuth here at 520.08. But if you solved it counterclockwise, you might have had 160.08. What do these two things look like? What's that look like their difference by? 360? 360? This is a real big azimuth for that direction. This is 160. They're just 360 degrees difference than each other. So same thing, just as we're adding that 180 each time. Sometimes you add, sometimes you subtract. So, but they're both right. I mean, that azimuth and that azimuth they're the same. But you can see here, we went clockwise on ours, so the forward azimuths were all going in this direction. On this one, when you go counterclockwise, the forward azimuths were all, this was a forward, this was a forward, this was a forward, because you're going in that direction. But the angles are, the actual azimuth numbers, numerically, they're the same. All right. So how about this? I'll extend, how about this? I will extend the homework assignment, the due date. Does everyone have a lot going? What should I push it to? Tuesday? How about I take what's due today and I'll push it to Tuesday at 6? I would like to just have everyone work through. Getting from yourselves to a level of comfort where you're at like a 8 or a 9. That's the goal. Get to an 8 or a 9. This isn't something you're going to do a lot in the rest of your career, and I understand that. I don't want to turn this into a big assignment. So it's just understanding how to work through the cadence of that. Okay? So let's do that. So I will move it. I'll shift it back. All right. Let's do this. I know it's a little bit early. Let's catch a break here, and we're going to move. We're going to use this concept and start getting it to where we can get coordinates out of this stuff. So let's catch a 10-minute break. And if while we're out, if you have questions or want to shout at me or something, just please feel free to ask. Something that can crush it. That's the general theme. That would mean the latitude from point A to point B changed. Let's go here. This is, just so we can put a visual to this, it's 53.20 feet. That's how it sizes up. We took the cosine of the azimuth times the length here, and that gave us the latitude. Latitudes in this column, latitudes up and down, north and south, so we got it. Let's do the same thing. So what does the table say for the departure? It's going to be this direction. So what is the departure? It says take the sine of 7111 times 164.95. Punch that in, see what you get. And it is, like I said, it's good practice to work the calculators, and the more you punch them in, the quicker you get. Numbers? Who's got something?
What was it? You gotta multiply it?
Yeah, so it'll be the sine of the angle times the distance.
156.13.
Brendan says 156.13. Shakes the heads.
Yeah.
Kenneth, yeah. Eduardo, shakes. Leandro, Vinny. 156.06. Vinny, check your. Either see if did maybe a length in there. Your calculator is in rectangular coordinates, right? It's not. I know sometimes you can just punch a button, or it could just got a digit in there somewhere too. So I'm hearing 156.13.
Yeah.
156.13. And let's do this. Both of those came out as positives, right? So let's go ahead on both of those and just keep a positive sign there. So what's that saying? It's saying we got a positive 156. So what does that mean? On this sketch here, we are 156. Oops, 13 feet. So to move from A to B, just by using the formulas, it's saying we left A, we went to the north, we went positive by 53.20, and then we went to the east by positive 156.13. Does everybody see that? That's an anchor. So shakes of 9 heads. Everybody needs to be able to see how we took this table and got moving, because really that's what we're doing in this is we're going around the box. We're gonna build a box, and that's how these will change. So we went up 53, so we went to the north, it was positive, and we went in this direction to the east, it was also positive. Okay, let's go to the next one. Let's go to B to C. So what do we think is going to happen? So B to C is doing what? B to C is moving in this direction, so we think it's going to have a positive label. But what's happening here? the latitude, which way are we going to go from going to B to C? Down. So we're thinking this negative, it's probably going to start shrinking, right? So let's go ahead, do the same calculations in here. So let's go ahead and figure out the latitude, which is the north and south, for B to C. So same thing, just follow the formula that's in the table. Take the cosine, and you can take a cosine of a big angle. That's what's kind of neat about using azimuths. You don't have to worry that the angle is bigger than 90 degrees, even though we're solving for a triangle. You can just punch that in. Punch in 149 as your angle, and take a cosine of it. And then go ahead and multiply it by 8841.
75.78.
So Brendan says 75.78. Got a negative?
Yes.
And yours was negative. Okay, so yeah, Brendan, that's why I left that. So the negative 78, the negative is a keeper. We want to hold on to that. So it's negative 78. And that's good, right? Latitude, ladder, up and down. We're heading down because we're heading in that direction. So minus, this is going to end up being minus 75.78 feet. Because we're going in that direction. So let's go ahead, keep going. So 149, let's do the departure. So take the sine of 149.
45.53.
8841. I'm punching mine in here too, Brendan. 8841. Just doing a check. 4553. 4553. Okay.
Yeah.
Positive or negative?
Positive.
Positive. Okay, so we'll keep it plus. 4553. 4553. Okay. And everybody sees we're going from B to C, so we're heading to the east. It's getting bigger. Positive direction going this way. And like we said, the latitude, we're dropping down, so that's why the negative. Just keep carrying the signs. Whatever the angle of the azimuth is, just let it be your guide. Okay, I'm losing the page here. All right, let's go ahead and work, let's work C to D. So same thing, big angle over here, 224.18. Let's take the cosine. And then you'll be multiplying it by the length. 121.69. Shout out some numbers when you get them.
Negative 87.09.
Anybody else? Head shake, Eduardo, shake. Zach, you're rolling back there? You good? Cynthia? Okay. So minus 87.09, and we're going to keep that sign. You guys are starting to see you're seeing the pattern develop now. So we're dropping, we're continuing to go south. So that would mean that makes sense that this is 89, 87. That's bad. 87.09. All right, do one more here. So departure. So let's take the sine of 224.18. 18, I gotta get 9 in. Say it again, Brendan. Anybody? Brendan, I thought I heard a number over there.
84.99.
84.99. Positive. Let's say this before you look at your negative. Yeah, negative because of what we're heading in this direction, so it should be negative. That's really the kind of neat part about this is we don't really have to think if it's positive or negative. We're just letting the azimuth do the work for us. It's already going to, by punching that into the calculator, it'll tell us what direction we're going. So we had negative 84.99. Okay, let's do this. Everyone, just take a couple minutes. Go ahead and solve the next two. Solve D to E and then E to A. Just go ahead and punch those in on your own. Vinny, is your calculator, how are you doing on it? I
When I got negative 84.59.
84.59. Let me try this, Vinny. Are you converting the angle from degrees and minutes into decimal degrees?
Yes.
Or does your calculator allow to just put in 224.18 and let it give you the... I'm just wondering why there's that little... How did you do on B to C, Vinny?
Those are fine.
Those were fine. Probably because we were at 0 minutes. So I'm wondering maybe it's that slight 224.18 isn't the same as 224.18, 18 minutes. So I wonder if it's just degrees and minutes and how your calculator's thinking. And then I don't know if anyone's keeping track the way that I'm doing it, but if you want to transfer those numbers over onto this sketch like I'm doing here, just so when you're working at home or working on the next problem, one of these, I'm going to do the same thing. It's just departures and latitudes on the sketch. Okay, everybody caught up? That's your numbers. If you're still punching them up, I've got them written down here on the table, so we'll sum them all up. So we have gone around the box of the shape. I'll slide this over here. So we've gone around the box. Now, how about this? In theory, if everything was perfect, this was a perfect traverse, what do you think if we left A, and we'll just go around this shape here real quick, and let's follow the box. If we left A and we went 156.13, we went another 45.53, and then we came backwards, 84.99, another 108.03, and 8.75. If I added these all together, plus, plus, minus, 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 what should I get?
0.
0. Does everybody see that? If I started, I'll run that one more time. If I started at A, and everything's at 90 degrees, so we just went around a box, and I took this departure to the east, kept going to the east to get to C, and then I came backwards. C to D, D to E, and then E to A. As Brennan said, it should be 0. It should total 0. So, does everybody see that? That's what we're shooting for. If this was perfect. Same with the latitudes, right? If we were A, we went up to get to here. We came across, we went down a negative, came across, we went up a positive. Those should also be 0. So we already calculated all 5 of the interior angles. Those all add up to 560 or 540. What happens now if we take the table and do just what we said? Let's add up these 2 columns. And if the traverse was perfect, if the distances that we shot as a crew were perfect, these should sum up to 0, right? The columns should sum up to 0. Let's add them up and see what you get.
got 0.13 and 0.11.
How are your signs on those, Brendan?
They're both negative.
Both negative? Let me double check. Let's see that 53.
We know the 0.3 was positive, but the 0.11 was negative.
Okay, that's what I was checking. We'll let everybody catch up. Brendan's on it. So in this case, I saw plus 0.13. And over here, I saw minus 0.11 feet. So if you add them all up, we have a delta. So the box didn't close. So that means that the 540 degrees worked out well in the traverse, but something's not perfect with the distances. And that's what this is showing us. Okay, so Bob, what do we do with it? We can fix it. So, Bob's crib sheet. This one is a good one for the binder. This one is a good one for everything that's pretty much doing here. So there's some terminology that we can talk about. The issue right now is 540 degrees worked, but the distances didn't. If we want, we can adjust. And that's what we're gonna kind of learn how to do now is how do we adjust this traverse so that it balances, so that we do get to having angles and distances that make this a perfect square and a perfect traverse. So there's a couple of factors on your sheets in the book. The book kind of explains it. One of the terms we're going to talk about. Is there an extra? Zach, is there one left? I'm going to grab that extra one from you. That's for Brian. I got to keep all these things in Brian. Oh, just the one. Oh, these are all extra. So there's a term that we call the linear error of closure. This is kind of statistic based, but if you look at that formula, the linear error of closure, it's kind of a play on Pythagorean's theorem, but it basically says in this box, if we were to take the sum of all the latitude delta and the sum of the departure and take the square root of it, you see that's Pythagorean's theorem, right? It's essentially saying, how did this triangle work out? So when we take a look at, and we call it the linear error of closure, we can do that. So let's just run this formula real quick because we're going to use this number. So over here, we're just going to say linear error closure. And that's going to equal the square root of 0.13 feet squared plus minus 0.11 feet squared. Run that number out, see what you get here real quick. Calculator. Anybody got it?
.06928.
Running at 0.06. I got something slightly different. Let's see here.
Wait, no. See where the calculator messed up.
Did you get it? It's always the calculator's fault. 0.17 did I hear? Or that's what I had.
Yeah.
That's what I had too. Okay. Okay. So we got 0.17. So that's just a factor. It's just a factor. If you look on the formula crib sheet, the next factor is the precision. So the precision is how good was this? How good was this traverse? If it was us as a new crew and we were out in the parking lot running this, we might get a little different. We might do a little worse job than a professional land surveyor that does this every day for the last 25 years. We're going to get different numbers. So on the formula sheet, we're going to use the term precision. So the precision is that linear area of closure divided by the perimeter. It's basically a statistic. How good is it? If we said, how good were our latitudes and our departures divided by the whole perimeter of how long it took us to get around the shape. So let's go ahead and just add up the 5 distances here. This is the distance of A to B to C to D to E. What's the total distance it took us to go around that traverse? I'll drop that in there. I got 559.36.
That's what I got.
That's what you got. Okay. So let's just think about this practically. We had these latitudes and departures, and we were what, a tenth and a tenth off over a shape that was, I don't know, how big was this? 250 feet. So I don't know. It would fit within the parking lot out here, out front. So if in the distances and the shots we were a tenth and a tenth off, all right, what's a tenth? Tenth is that. Not too bad for that whole perimeter of 560 feet. So let's use the formula. Let's just see how it turns out. So precision is the linear area of closure divided by the perimeter. So the precision of our work equals the linear area of closure, which is 0.17, divided by 559.36. Let's see what we get there. You get some really small number, right?
Oh, 0.003.
0.003, and there's some digits behind that. That are probably they're buried in our calculators, but I got 4 digits, so I got the same thing. 0.03, there's more numbers in there. There's one way to flip. You guys have the key on your calculators, the 1 over x. Does everybody see the 1 over x on your calculator? I think everybody should have a 1 over x. The way that we can record this, or to speak of it so that we can all not have to deal with, hey, my precision was 0.00003. If you flip the precision around, and I'm just going to show you the factor, take 1 over x on your calculator, and what do you get? I can show you on mine. It's this function right here. It's this little 1 over x. I think everybody should have it. Or if you can't, you can take 1 divided by this number. That's the way you could do it too. But the number that I got, and what it does is it converts it. It just says 0.0013 is 3284. Did anybody else get this? You guys see that number popping up on your calculator? 3284. Something kind of close to that. So it's a ratio. That's all it is. It's taking that small decimal and just making it a ratio of 1 is what it is. So essentially, our precision and the way we would record it is we were 1 in 3,000. 1 in 3,000 is how we would kind of call that. 1 in 3284. And on the crib sheet, you can kind of see how tight the precision should be. So for a construction survey, if we ran this traverse and came up anywhere between 1 over 3,000 to 1 to 10,000, that's okay. But if this was a professional land surveyor, it'd have to be a lot better. So it's kind of scary to think that for this length of the traverse in the parking lot, by us missing by a tenth and a tenth, we're just kind of good. It's just, this was okay. It wasn't land survey grade. It would have to be really tight to have 1 on 10,000. So that's just kind of just to give you a basis of how good this is. So we're okay. I mean, it's all right. We're still going to balance it. We can still calculate it, but this was so-so. Okay. The next calculation we have to do, and it's it's another concept. Look on your formula sheet there, and you're going to see something called the compass rule adjustment. And the compass rule adjustment is basically also just statistics. I don't know if we're at a good break point here. 35. Let's see if we can keep going here. It's statistics. What we have to do is we basically have to say this point 13 and this point 11, how can we mash those around? How can we average those, mathematically average those, to be able to spread this point 13 over these 5 distances? That's basically what we have to do. We've got to take this leftover 1300ths and we want to push it back into these results so that it comes out that this sums up to 0. And that's what the compass adjustment is. It's basically just taking this and averaging it. So what does the formula say? Let's just look on the compass rule formula. So for our latitude, we're going to correct. So we're going to put some very small numbers inside of this column. And those small numbers are going to end up being taking this point 13 and factoring it. We want to factor it. So what do we do? What does it say to do? It says we are going to take that sum of the latitudes, this point 13, and we're going to multiply it. We're going to multiply it by the length of the segment, which is this, divided by the total length of the segment. So just in your calculators, real quick, let's just do this. What is 164.95? 164.95, this guy here, divided by the total perimeter, 55936. Oops. 559.36. 0.29, is that, I heard 0.295 maybe? Is that 0.295? So let's just think of this. Think of a percentage right now. We know that this is the total length around the shape. We just grab this length. So it's basically saying that this is 29% of that. That's just kind of easy math. We're just a ratio of this portion of the total, and it comes out to 0.29. So it's a percentage of that. So the formula says, let's just use this 0.29. It's 29%. And just times it by the 0.13, the sum of this latitude. We're basically saying this length AB contributes 29% to the whole traverse. What is it times 0.13? 0.13.
0.038.
0.038. And let's go ahead and we'll round it up to 0.04. 0.04. So let's do the same for BC. What is 8841 of 559.36? What percentage is that length of the total traverse? 8841, 559.36 divide 0.158. So it's basically, it's short. It's another 15% of the total. So let's use that 0.158. Let's multiply it by 0.13. Anybody get 0.02? 0.02? Does everybody see how I got it? Bob, I didn't see how you got it. Everybody see how I got it? It's the 8841 divided by this, so it's the ratio, it's the percent of that length times the missing 0.13. So let's go ahead and you can solve the next three then. So 121.69, 559.36 times that. So I can see already, so I'll just, this is easy math here, so maybe we'll just do a quick math check here. So 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. It's kind of summing up. Basically what we've done is we've taken this 0.13 and we figured out what percentage each of the lengths is, and we've made that factor for it. That's all we've done. Just so we can do the same thing for the departure side. What was our total miss on the departure? Was this 1100ths, right? So the 1100ths, we're going to do the same thing. What is this percentage of the 164.95 of the 559.36? So we can punch that in, 164.95, 559.36. So that's that 29.5% we were talking about. But this time we're going to multiply it by this. So we're going to take this 0.11 and we want to spread this out. We want to spread that out on all 5 of them. So this is 0.03. Is anybody not seeing how that comes together? So go ahead and just keep. Let's run these numbers out. It's good practice to just punch in. So B to C, 88.41, 559.36, and we're working on this 0.11. So we're spreading that 0.11 out.
Why is it not negative?
Good question. I will. You are on it. We're gonna hit it after we get all the numbers in, Lisandro. I've been purposely not putting any signs on it. So when we get to we'll get all of our numbers calc. We'll talk about the signs. Great question, Lisandro. It's a great question. If you guys want. So I ran them out if you want to grab them off of the... Getting comfortable with the calcs, it's just punch them in your calculator so you can check against mine. Okay, so everybody's got the table set. We've got our raw numbers in. So Lisandro asked a great question of why not the signs? What are we doing with the signs? So when we run these out, I purposely didn't put a sign on it because we want to think about what we're going to do here. In this case, what happened with all of our latitudes? What did we end up? We ended up what? Positive? So it was too tall. We ended up, we had too much. So what do we need to get rid of that, right? We need to get rid of that. So the sign of this is going to be, what do you think if we had to get rid of this? We would want all these to be what? Negatives. Negatives? Does everybody see that? We were too big. Our total latitudes and all the summaries were too big. So we want to get rid of that. So in this case here, we want to be deducting all that. And if we added all these up, I think we got 0.14. We put a negative sign on it. So the comparison, in theory, these are the same numbers. It should be 0.13, just some rounding in there. That's why it turned out the way that it did. And how about the departures? So what happened when we did our traverse? We came up short. We were minus 0.11, so we're short. So what do we have to do? We got to push that back in, right? We've got to make up. We want to get that missing 0.11 back in, so we can go ahead and call these pluses because we want to bless you. We want to push these. We want to push this back in. So I add these all up: 3, 5, 3, 5, 7, 9, 10. Again, just with some rounding. That's okay. The hard part is over. That's it. It's really following the table and making this adjustment. That's really what it is. Now, what can we do? What do we need to do with these numbers? So let's think about it. We figured out that we were too big in one direction. We were too small in the other direction. We now figured out what we need to push in or take back out to get them to 0. So we have what's called the balanced latitude and the balanced departure. In this case here, this was the first latitude and departure we did with the length, and let's just say with the bad lengths, the lengths that didn't work out, we're making these two adjustments to now make them work out. So all we have to do here to get the balanced latitude is let's take the latitude that we have, 5320. Let's take away this 0.04, so we're going to shrink it. We've got to shrink everything up, so let's shrink it. So 5320 minus 04 is going to be plus 5316. Everybody see how I got that? 5320 minus the latitude adjustment to that. And we can run right down the tables and follow the signs. Let the signs work the way they do. Minus 75.78. 75.78 negative. Minus 0.02. So this, just everyone kind of check your signs in that. See how this is, 75.80 feet. And we can take, well, maybe we take a look at this as a group here. So our latitude was actually a negative because we were going down, but we still want to honor the sign of the adjustment. We still have to shrink it, so we should get 75.80 for that one. So we'll keep moving on here, keep doing the same thing. That's plus. Letting everyone catch up. So what do you think happens now when we added our latitudes up to start? We were 1300ths off. Well, we balanced it. What do you think should happen when we add all these up?
0.
Should be 0. Guys, I agree. Let's sum up that column and see what we get. So tally this all up. If everything worked, it should be 0.